Hello, welcome to today's group class live, or from the master classes from inside, or if you're joining us from inside the PE portal. This lesson today is going to be focusing on, well, two separate lessons really. We're going to merge them into one today, and we're going to be looking at the pathway of air, so the respiratory tract, and we're going to look at the gaseous exchange, so how oxygen can get into our body and CO2 can get out of our body, and the role gaseous exchange or partial pressures and diffusion gradients and the role of the alveoli, all of the different factors at play which allow this exchange of gases to occur. But before we get there, we of course need to know the structures which make up our respiratory tract, which is where we're going to start today. So in this lesson there will be an opportunity to use the resource sheets, which you can get over on the trial portal, actually on the GCSE portal.com, or sorry, GCSE portal.com. And if you just log in and set yourself up with a trial portal account, and you'll be able to access this video on demand, flashcards, you'll be able to get the resources and the worksheets which we'll be referring to in today's lesson. So without further ado, we will get started with our first topic, which is the pathway of air. I want to get the right one up here. There we go. So the pathway of air. So before we go into the structures, the names, the terms, how to label, what we're first going to take a look at is sort of what the cardiorespiratory system is. And if you are obviously in a lesson or classroom situation, then there is a bit of a starter activity for you and your classmates or you and your cohort to do. But obviously online today we won't be doing that. But what I wanted to quickly say was sort of what is the cardiorespiratory system? Why is it important that we know about it in terms of sports performance, in terms of training, and in terms of overall health? So I'll quickly leave this slide up here for you to just have a look at. So things that you will learn about within the cardiorespiratory system. Okay, not necessarily just today, but just within this whole unit. Where does it sit in terms of our bodily systems and the specification of your exam? So we will be looking at the route the air takes to get in and out of the body. We'll be looking at how oxygen is passed in and out of our body, and CO2, how that's passed in and out of our body. Then once these gases, or oxygen makes its way into the body, well, we need to know about how it gets around the body. So the blood vessels that actually transport the blood, which is another component of the vascular system. And then we're going to take a look at the heart. So how the heart pumps the blood that carries oxygen and carbon dioxide and nutrients from different areas in the body so that we can function in sport. So that's the big picture. How our lungs, our blood vessels, our blood and our heart can all work together in order to supply our body with the appropriate nutrients for it to actually exercise and for it to sustain itself. Okay? So today we are going to look at the pathway of air, and then obviously later on, or halfway through this group class, we will be then looking at gaseous exchange at the alveoli. So to start with, we are going to be able to state the 6 components of the respiratory tract. So the 6 different regions or pathways that air goes through. Okay, we're not talking specifically about oxygen and carbon dioxide at this point. We're just talking about outside air, how it comes into our body. So what route does it take? And then most of us should be able to describe or explain in a little bit more detail features of these 6 components of the tract which allow it to function as it does. So what attributes do they have which assist our body in getting this air in and we use it? So I always draw this analogy between the respiratory tract and a hoover, because a hoover, in order to actually suck things up off the floor, it obviously has to suck in bodies of air, volumes of air at high speeds, and that high speed movement of air is then what drags particles with it, and obviously we can clean up dust and particles and dropped food or whatever it might be. We can start to suck this air into this mechanism. And there's lots of different parts to a hoover. It's a complex instrument. It's got many different moving parts, things that rely on one thing to do a certain job so that the next part can do its job. And if one of these parts fails, then the whole system is likely to fail. And it's similar to our respiratory tract. Each one relies on the other to do its job properly. If one of the parts of our respiratory tract fails, or there is an issue with it, or it's damaged, or poor lifestyle choices might cause infection or damage of it, then the air pathway as a whole system is beginning to falter as well. And what's important to note is a hoover doesn't magically bring this air in. It's not just it's very easy to get or to overlook the fact that we press a button and things happen, things change in order to cause air to move. When you take a breath in, you might just think that you are literally drawing air in, sucking air in. But there's physics involved, there's science involved, there's laws which actually have to take place in order to move air from one place to another. And that's where pressure comes in. So a lot of what not necessarily the air pathway, but for gas exchange and for ventilation, we talk a lot about pressure. And before we go any further, I want to make very clear that there are two different types of pressure. Okay? Air pressure, sort of macro air pressure, okay, the larger term is to do with how many components or how many particles there are in a certain space or a certain volume. Just like in a classroom, you might have 30 students in a classroom. That's the pressure of that classroom space. Now, if there were 50 students in that same classroom, the pressure has gone up. You're closer together. There's a little bit more tension. It's a little less inviting perhaps, because there's more people in the same size space. Now, if there were 50 people but in a bigger classroom, it would feel the same as 30 students in a smaller classroom. So pressure it's relative to the volume. Okay, so it's twofold. It's how many particles are in a space and how big that space is. So if we change either of those things, the amount of particles or the size of the space, we can change this macro air pressure. Now later on, we're going to be talking about partial pressure. And all I'm going to leave with you at the moment is partial pressure isn't necessarily the number of students in the classroom, but it's the ratios of the students. So if we had 30 students in a classroom, that's the total air pressure. Partial pressure could be there are 15 boys and 15 girls. So the partial pressure, the part pressure of boys is 15 out of the 30. It could be the partial pressure of those still wearing their blazer. Only 5 out of the 30 have their blazer on. So the partial pressure is 5 out of the 30. Now the space hasn't changed, the number of students hasn't changed, but it's the ratios of the different parts that changes. So that's what I wanted to sort of get out there at the start. There'll be two terms, air pressure and partial pressure. They're not the same thing. And to start with, we are going to be talking primarily with the air pathway. We're going to be talking about air pressure as a whole. Okay, partial pressure we'll leave for later on. So, air pressure. The system inside of our body works in a way that we change the different air pressures inside of our body in a way to draw air in. Okay, we don't magically just suck this air in. We create changes to the space inside of our body, which changes the air pressure inside of our body, which then invites new air in. And we'll cover why later on. So, the pathway of air, very simply, it's the route that air takes when we breathe. Okay, the route that air takes when we breathe. It starts around us in the environment and it ends up inside of our lungs. And when we exhale, the air inside of our lungs leaves our body through the same pathway and then back into the environment. Okay, so think of this body of air, this volume of air, almost like a bus. Okay, it's the carrier of things like oxygen and carbon dioxide. There's lots of different types of particles within air. Some of them are oxygen and carbon dioxide. So when we breathe in this total volume of air, that stays sitting there, that bus parks up, some oxygen jumps off, some new CO2 jumps in, and then we get rid of it again. Okay, but it's this pathway of air, the route that this volume of air takes. And we've got these 6 main components, and we're going to go through each of these individually, but just to sort of say them right now, we've got the mouth and nose, we've got the entrance, we've got the trachea, okay, this main pipe that runs down through our neck. We've then got inside of our lungs, or what delivers it into the lungs, we've got our bronchi. And then once air has gone through our bronchi into our lungs, we've got alveoli, these tiny air sacs, these bubbles, which actually accept that air. So nose and mouth, and if you are going to write things down, these are the 6 you need. Now is that on this slide? Yes. There is a resource sheet, like I was saying at the start, at GCSEPeportal.com. You can download the resources that go alongside this lesson. If you've already got it, fantastic. Now's your time to be writing these 6 terms down into that component column. And as we go along, you can be filling these out and making notes as you go. So, number 1, the nose and mouth. These are the entrances. Okay, the entrances to the respiratory tract. They help moisten the air. They act as the first line of defence for our body. Obviously, when we're walking around, there could be, I know this very well, there's pollen in the air. Okay, I suffer from a little bit of hay fever, so when spring and summer does arrive, and there's a higher volume, there's a higher number of fine particles, parts of flour and pollen floating around in the air, they enter my body and they irritate my face. Why? Because my nose has filtered them out. My mouth has filtered them out. Okay, both of which, they're moist. They're there to help collect anything that flies in past them. If they were bone dry, or they didn't have tiny hairs inside of your nose, if we didn't have those things, then anything from the air would come straight in. They wouldn't get caught by our mouth and nose, and they would get further down into our respiratory tract. Now we've got no way of sort of scraping clean the inside of our respiratory tract, so it's important that we don't let things get in to start with. So our mouth and nose, they're the gateway, and they help moisten the air and filter out these larger particles that might be coming in this body of air. Second, we have the trachea. Now this is the pipe, okay, the airway that connects the back of our mouth and the back of our nasal passageway. As you can see, they meet, don't they? They converge. Those 2 grey pathways, they converge into this blue track, this trachea. Now it's not blue inside of our body, but it's blue on this diagram here, and it runs down through our neck. Now, an important feature, we could call it, of the trachea is that it's ringed with cartilage. So these thin rings, almost like calamari, that sort of shape and size, they ring our trachea and they help keep it open. But we've got this semi-rigid structure that it can respond to different movements. It can respond to some slight impacts. If you think about in a game of football, for example, if a footballer goes to chest the ball and they control it, but it bounces up again, we've got the rings of cartilage around the trachea to help protect it. Because if something hit it and this trachea collapsed in on itself, then no air would get through, or maybe not no air, but a limited supply of air would actually be able to make its way through and down the trachea. Going back to the analogy with the Hoover, if that were to happen, well, the rest of our components, well, they've got no air to actually sort because it hasn't made it to them because the trachea has collapsed. So it's ringed with cartilage for protection, and the trachea also has mucus or phlegm, as you might have heard it. It's one of the gunky stuff that you sometimes cough up in larger quantities when you're a little bit ill. And we've also got cilia, okay, which are sort of micro hairs, similar to nasal hairs, but even smaller. And these also line the inside of the tube, this track running down. And together, they help filter out even more particles, even finer ones. Because we already have the mouth and nose filtering out the big ones, it's almost like a sieve. We sieve out the big things, still some finer particles make their way in. Our trachea's mucus and cilia, they can help capture even these fine particles, pull them to the side, we can digest and get rid of them. So the air moves down this trachea and it now enters the bronchi. Okay, the two bronchus or bronchi for plural. Their main job is to divide this airflow. So we have this one pipe, this trachea coming down, we now need to diverge or divert this airflow. It converged, mouth and nose came into one pipe, and now we split the air again into two pipes, our bronchi. One goes to the left-hand side lung, one goes to the right-hand side lung. So we're dividing this airflow. In doing so, we can start to slow down the speed that the air is currently moving. And we'll talk more about that in a moment. More so for gaseous exchange. But bronchi divide this air into the left and right lung. Each one obviously leading to a separate lung, and then they split as well. They're also ringed with cartilage, but they start to branch off, much like, it looks almost like roots on a tree. They get smaller and smaller and smaller, reaching into all the far corners of the lungs. And the rings of cartilage, again, are there for protection, especially in this section, going back to that football control. Now that ball is compressing the lungs. Yes, we've got the rib cage and we've got the pectorals on top to help with protection, but there's still going to be an element of compression, especially in contact sports as well. American football, rugby, perhaps a stray elbow in basketball. The cartilage rings are there to sort of help with that compression, and then they bounce back and they keep these air passages open. Which leads us to bronchioles. Okay, these are the smaller sections. There we go. The smaller sections, so the end sprouts of the bronchi. Now these don't have cartilage. This allows them to be sort of smaller, and they can really spread into all of the crevices and the tiny spaces of the lungs. Now these are spreading out from the top to the bottom, right the way to the edges and into the centre of the lungs as well. And they carry on dividing the airflow up. Now it's important that we divide this airflow, because if we just had this one trachea pipe come in, well, all of that air is concentrated in one section. And what you'll realise when we talk about gaseous exchange is that we need opportunity. We need a large cross-section, or cross-sectional area as it's also called. We need to touch as much of the lungs as possible to stand the best chance of getting oxygen in and getting CO2 out. So bronchioles, we've got a high number of these, or I should say a higher number than bronchi. So these bronchioles branch out, they're smaller, they're thinner, they divert this air into all of the different spaces inside of the lungs. And at the end of each bronchiole, we'll come back to the lungs as a whole, at the end of each bronchiole, we have alveoli. Now, I always think of these, and I always draw the analogy to bubble wrap. Okay, that sort of composition of space and surface. Very thin layer with space inside for air. It looks a little bit like a raspberry or a blackberry. Now, these bunches of alveoli, each one almost like a little bubble, a little air sac. And it's at the end of a bronchiole. So the air which flowed in through our mouth and nose, it got filtered. It went down our trachea, it got filtered again. It then got split into our bronchi so that both lungs got a volume of air. The bronchioles then split this airflow into finer amounts, into smaller volumes, travelling at slower speeds, until the air reached the ends of the bronchioles and sits in the alveoli sacs, these air sacs. And this is where our capillaries flow past. Okay, see the blue and the red lines there wrapping around this alveoli bunch. And that is where gas exchange occurs. And that's what we're going to move on to a little bit later on. But these are surrounded by capillaries. This is where blood meets air. Okay, blood meets air. Not necessarily in a in a mixture, but this is where the blood is close enough to interact with the air, almost the outside environment. Okay, a fancy phrase for this is external respiration. We've got the ventilation bringing air in and out. External respiration is where blood can interact with this outside air volume. Now I did quickly whiz over lungs, so I'll go back to those quickly, just to sort of put it into context of where they are and their role. The actual, the lungs themselves, these almost carrier bags almost, with everything else going on inside them, but they hang inside of this thoracic cavity. Now the importance of that, you might be thinking, well, they just hold the alveoli, surely that's it. Well, not really, because they almost act like the, what's that instrument called? Is it a harpsichord? No, not harpsichord. An accordion, that's it. An accordion whereby you've got the different keys at either end, and it's almost like that slinky action. And if we increase that, obviously the space inside of that accordion expands, and everything inside changes. Well, that's what happens with our lungs. They're the bags which are dragged around and they're expanded or compressed. And in doing that, look at that last point there, this causes air pressure to change inside of them. Going back to the beginning of this lesson, there's two types of air pressure, the big sort and the partial pressure sort. Now the big sort, that's where we were talking about the classrooms, 30 students in a classroom versus 60 students in the same classroom. That's a high pressure environment. Well, by expanding the lungs, what we're doing is changing the space. We're changing the volume of the lungs. So using that classroom analogy, if we had 30 students in a classroom and then miraculously dragged the four walls of the classroom out and left the 30 students in it, well, because we've now got a bigger space and the same contents, the pressure has dropped. Those 30 students would now have more space to float around. They'd be less likely to bump into each other. That's a low pressure. So what we've just done, if we drag these lungs around and we pull our rib cage upwards and outwards using our respiratory muscles, which we'll cover again in a different video, but if we can drag our rib cage and expand the lungs, expand the space, and we can drop the pressure inside, we've now got a lower air pressure inside the lung compared to outside of our body. And hopefully what we know by now is that air moves from area of high pressure to low pressure. So by creating a low pressure environment inside of our lungs, inside of our alveoli, because we've dragged them out and increased the space of them, we've dropped the air pressure, high pressure outside of us, low pressure inside of us, air is drawn in. Air moves from areas of high pressure to low pressure, and we've just ventilated, we've just inhaled. So we don't magically suck air in, we drag our lungs around We contract muscles to pull the rib cage, which then pulls and opens up our lungs into bigger spaces, which drops air pressure, which invites new air in. So there are activities for you to do. If you haven't got the resource sheets, then just note these down, or maybe sketch a quick drawing of a person. But yeah, just label those 6 components onto that diagram. And there's also another activity which it could be a bit of a fun thing to do, but take each of those key components and come up with some sort of rhyme or term or phrase or something which sticks in your mind. Okay, try and come up with a phrase or a saying that allows you to remember the root of this air pathway or this respiratory tract, because it'll be far easier to remember a funny phrase than it will be to remember 6 or 7 or 8 separate terms in a certain order. Okay, so they are activities, and hopefully after that you will now know the 6 components of the respiratory tract, and you should know the different features of each which allow it to do its job, which that sort of brings to the end that part of this lesson. So the pathway of air, which was the first one from the cardiorespiratory system. So what we'll do now is move on to the second part of this session, or for this group class, which is gaseous exchange. If I just quickly click on to that one there, perfect. And we are on this presentation. There we go, perfect. So, next part, so about halfway now, gas exchange. What will we know by the end of this part of the session? So, all must be able to identify the fundamentals. We've already touched on them to do with the partial pressures, but we'll know the fundamentals behind gas exchange and be able to label a diagram, just with the key terms. Hopefully though, most of us should know how haemoglobin plays its part, and the things to do with each component and the role they play, but some of us, or some of you I should say, should know some of the key features that affect gaseous exchange. So what different factors are at play which determine the rate of, or the success of gas exchange occurring inside of the body. So to intro this whole thing, we almost need to start, I'll move that up there we go. We almost need to start with energy, almost a justification as to why we need gas exchange to occur. Well, in order for muscles to contract or cells to repair themselves, we require energy. Where do we get energy from? We get it from food. Well, how do we release energy from food? Well, there's a number of chemical processes that go on, but simply glucose from food plus oxygen, with a few enzymes in there as well, which are catalysts for change. Glucose plus oxygen plus enzyme activity leads to the release of energy. Leads to the release of energy from foods. All of those energy bonds holding the carbons and the hydrogens and the oxygen molecules together in the form of a glucose or a carbohydrate or a free fatty acid. Those energy bonds are broken down if we stuff oxygen into the cells that hold this glucose, and the enzymes get to work, and bang, we release energy. And that's the energy that fuels muscle contractions. It fuels our repair of muscle tissue. It fuels the resupply of red blood cells inside of our blood. What are the downsides? Well, maybe not downsides, but what are the byproducts? Carbon dioxide and water. Just like if you were having a bonfire, you can convert a block of wood into light, the flame. How? Well, it's wood plus oxygen plus heat, and we get the light, but we also get heat and smoke. So even though light was the primary reason we did it, we had the byproducts of heat and smoke. So even though we break food down with oxygen, and the primary reason is so that we have energy to fuel our bodily processes, The byproducts that also occur is carbon dioxide production and water production. So what's this got to do with gaseous exchange? Well, we've just looked at in the air pathway lesson that we bring in this body of air through a certain respiratory tract, so it sits inside our alveoli, these air sacs, and inside that air we have oxygen. So that's where it is. We now need to work out how to get the oxygen from outside of us, from this outside air, into our body, and also how to get carbon dioxide out. Gaseous exchange is how we achieve that. So gas exchange, put simply, is an exchange of gases at a particular place at a particular time. Now today we're going to be looking at gas exchange in the alveoli, but it also occurs at the muscle mass. That's content for another time. But gas exchange, where two different gases can switch places at a certain place and a certain time. So in the body, what we're going to be looking at today, oxygen from the alveoli switches place with the carbon dioxide that's in the capillary. So oxygen goes in, carbon dioxide goes out. We've got this switch, this exchange of gases. Now the process of that switch, yes, it's called gas exchange, but how does that gas move? That's called diffusion. When gas moves from one area to another area. Okay, diffusion, where gas moves from one area to another area. So although this is liquid, okay, diffusion doesn't happen in liquid, or not in the context of gas exchange at least, it sort of helps paint the picture, because you can't really see gas, but you can see these two glasses of orange juice. Now, if you were to make a strong glass of orange juice and a weak glass of orange juice, or orange squash, let's call it. So we pour in the Robinsons into each one, but in one glass we put in double measures, and in the other one we put in a half measure. We top the rest up with water, so there's the same amount of juice in each glass, but the concentration of the orange squash is different. So what we've just got here is a difference in concentration. There's more squash, going back to what we said earlier about partial pressures, there's a higher concentration, there's a greater ratio of orange squash to water in the glass on the left side there, compared to the glass on the right. Now it's all relative, because we could put a third glass to the left of that strong one, which is even stronger. So diffusion happens when there's a high concentration of a particle in a mixture next to a lower concentration of a particle in a mixture. Okay, it's to do with concentrations, the amount of a certain particle within a mixture. And in terms of gas, if we breathe air in, okay, that's got well, depending on your environment, it's got a set amount of oxygen concentration in the mixture of air. So we breathe that in, and we now have that body of air with a certain concentration of oxygen inside the alveoli. It's now next to blood, which has a lower concentration or partial pressure of oxygen. So we've just created this thing called a diffusion gradient, where we have a high concentration of oxygen inside the alveoli and a low concentration of oxygen inside of the blood. And just like before, with pressures, things move from high to low. So to recap that, diffusion is the movement of gases between areas of different partial pressure. Partial pressure is how much of one type of gas there is in a mixture of gas. So if we were to compare two volumes of gases, if there was one volume with a higher concentration compared to the other, then we would see movement of that gas from one volume into the other, from high to low. And that difference is what we call a diffusion gradient. So if we look at oxygen diffusion, actually in a picture, well, the air that fills the alveoli every breath, it's got a lot of oxygen in. It's got the maximum amount. So it's got however much oxygen there is in the air at the moment. That's the same concentrations that we have inside of our alveoli every breath. But the blood returning to the lungs has a lower partial pressure. Why? Well, that's what we looked at a couple of slides ago. Because we were pumping oxygen into the cells with glucose to release energy. So we were using up our oxygen stores. We were depleting and reducing how much oxygen we had in our blood in order to release energy. So whenever that blood ends up back at the lung, there's less oxygen inside of that blood because we've used it up. So there's a diffusion gradient created between these two areas, the alveoli air and the blood, the capillary blood returning to the lungs. So what you can see here on this diagram, this green arrow, this shows you the direction of movement. So towards this top part of the capillary, there's very few oxygen particles per milliliter of blood. Why? Because we've been taking them out, because we've been using them for energy. So we've got low amounts, they flow past the alveoli, which is stuffed full of oxygen, so oxygen hops out. It exchanges with the CO2, which we'll come to in a moment, but it diffuses into the blood until it balances out. I use the example of going back to a classroom again, but if you had two classrooms next to each other, separated by a door, and that door was closed, and there were 50 of you inside classroom A, and in classroom B next door, there was only 5 people. Now, as soon as that door opens, the majority of people will move from the busy, high-pressure classroom A, they would move through that door into classroom B, where there's more space to be had, until there was about 26 or 27 or 28 I should say, students in both classes, because they balanced out. There's no need to move in between the classrooms because they're the same. They've become balanced. And that happens inside our alveoli and capillary as well. So oxygen will leave the alveoli until there's as much oxygen in the blood as there is in the alveoli. Carbon dioxide is the reverse. So we'll sort of talk through this picture first and then we'll look at the words. But look at that blood returning from the rest of the body. Look how much CO2 there is. It's packed full. Why? Because we've been producing it in our muscles. Because we needed the energy to move. Think about that fire. We burn the wood, we get the light, energy for movement, but we also get the heat and the smoke, the carbon dioxide and the water. So we've been producing large amounts of carbon dioxide which get stuffed into the blood so that we can get it out of our body. So we've got large amounts of carbon dioxide, higher amounts, higher partial pressures of carbon dioxide in our blood compared to how much carbon dioxide is in the volume of air that's currently inside of our alveoli. So the air that fills the alveoli every breath has a low partial pressure of C2. There isn't that much in the environment around us, not compared to how much there is in the blood that's returning to the alveoli at the moment. This creates this diffusion gradient, this difference of high pressure area and low pressure area. High pressure diffuses its gas into the low area or low pressure area. So there is an activity sheet for that one. A couple of questions just to summarise everything that we have done there. If you do have the activity sheet, fantastic. If not, then pause this if you can. If you're watching this on repeat, or if you're watching this live, then perhaps either wait for the repeat, or hopefully you were making some notes there as well. But yeah, the activity sheet is there to help you sort of compartmentalise and stencil out the different stages of gas exchange. There's also a blank diagram for you to have a turn at labelling as well, making sure that you get those key things on there: oxygen, CO2, haemoglobin, which we'll cover now in a moment, oxygen diffusion direction, and CO2 diffusion direction. So have a look at those if you get the chance, but we're going to move on. We're going to go on to the last part of today's session, which is, well, the main factors, these 5 factors that affect gas exchange: the rate of it, the opportunity for it, and how much of it happens. And the first one is haemoglobin. Now, haemoglobin is what carries oxygen. Okay, it's the I've already said that I've already used the bus analogy with the volume of air, but inside the blood, think of the haemoglobin as a car. There's only so many people that you can fit inside a car, and with haemoglobin we get 4 spaces for oxygen. Okay, 4 spaces for oxygen. So as these haemoglobin, okay, these sort of protein compounds, these protein cells that are stored inside of the red blood cells, these components of the red blood cell, they can link up with and connect with 4 oxygen molecules. Okay? Now, when we do have a haemoglobin connected with oxygen, we actually call it oxyhemoglobin. So we have this transition really of deoxygenated haemoglobin coming back to the lungs. It then passes the lungs, it picks up new passengers, it picks up the oxygen until it's saturated with 4 new oxygen molecules, and it becomes oxyhemoglobin. And it's then ready to go off on its journey around the rest of the body and deliver it and drop the oxygen off at the working muscles so that we can release energy from food. So haemoglobin are the cars, these are the transporters of oxygen. So when blood is returning to the lungs, well, we need to make sure that we've got large amounts of haemoglobin. We need to make sure that the volume of our blood is healthy and it's maintained its composition. And when it does pass our capillaries, when it does pass our alveoli, I should say, inside of our capillaries, the haemoglobin is there to collect fresh oxygen molecules. So, first factor, which is key for gas exchange, is the number of alveoli count. And before we go sort of into what this diagram here is, first of all, they're spherical. Okay, the way I sort of try and describe it is, I've got a book here. Right, imagine that as a window. Okay, so that's a gap, and if you wanted to pass as much things through that gap or through that window as possible, what could you do? What could you do to make it easier? Well, you could either change whatever you're passing through it, you could change the speed that you pass things through it, or you could make a bigger window. You could increase its area. Now that's a 2D shape, okay? And in order to increase the amount of stuff that we can pass through that window, we need to increase the area of this rectangle. Now, obviously, alveoli, they're not 2D, they're 3D. But if we still wanted to pass things through the surface of the alveoli, what shape would make sense? Spheres. Okay, that's the most effective shape in terms of the volume and the surface area. It's the most effective shape to pass things through. It's the most of it. If it was a cylinder shape, less cross-surface, less cross-sectional area, less surface area. But with a sphere, this bubble shape, there's plenty of opportunity, plenty of space to pass things through it. Now why, or how can we increase that further? Well, instead of having one big bubble, like let's say one big balloon, where only the air on the very edges of that big balloon are close enough to pass things through the edge. They're actually in contact with the edge. So what's the way around that? Well, if we were to reduce the size of that big balloon and divide it up into lots and lots and lots of tiny ones, that's what's happening with our alveoli. So they're tiny, they're spherical, and in doing that, we've got this huge surface area. Going back to this window idea, that is surface area that we can pass things through. Now, if we were to take each individual alveoli inside of our lungs and we were to unwrap, think of it like a Terry's chocolate orange, if you were to unwrap that foil, that wrap, that spherical surface and lay it all out flat, and we were to work out what space there was to actually pass things through, it's about the size of half a tennis court. That's huge. We've got that size, window to pass and exchange nutrients through contained inside of our lungs. That's impressive. Doesn't matter which way you look at it, that is so impressive. 500 million tiny little air sacs, little air bubbles, each of these individual spherical wraps that contain a little bit of air close enough to the surface so that it can exchange gases from inside the sac into the nearby capillaries for diffusion to take place through. And it's that large surface. If you're going to write anything down for gas exchange and alveoli, they create this huge surface area through which diffusion can occur. It's just essential. It's one of the reasons why smoking is so harmful for the cardiorespiratory system and sport performance, because the inhalation of toxic gases which are produced when a cigarette and tobacco and all of the chemicals are burned, that getting inhaled, that can damage these tiny air sacs. Think about the width of the skin on an individual bubble wrap. Absolutely tiny. So imagine if you were to start popping some of those, suddenly we lose this opportunity to pass gas through it. So a large surface area because we've got a high alveoli count, because they're spherical in shape. What goes hand in hand with that, because it's one thing to have loads of air bubbles, but we need blood to exchange the gases with. We need the capillaries. Well, we've got a high capillary count as well. Capillarization of the lungs. We've almost got this, it's that capillary bed. If you've ever dealt with sport coaching, or you've got the PE equipment out from the cupboard before, imagine you've got that net basket with all of the footballs stuffed into it. Each thread of that net basket represents a capillary. And it goes beyond that, because we've got a capillary bed wrapping around almost individual alveoli inside. And these capillaries are supplying the blood next to the alveoli. This same blood which has got low amounts of oxygen in. Meanwhile, in the alveoli, there's high amounts of oxygen, and we've got this diffusion gradient. So we've got blood being transported to the alveoli with no oxygen inside, while the alveoli have got high amounts of oxygen, and we've got opportunity for exchange. We can pass oxygen through that window, and we've got a massive window because we've got tiny spherical alveoli air sacs, which if we were to unwrap, they cover half a tennis court. 500 million air sacs. So I realise I didn't put those comments up, but I'll leave those there for a second. Capillaries, small blood vessels. They're narrow. They divert blood all around the alveoli through what's called a capillary bed. Now, something which we haven't really spoken about is, because there's so many capillaries, the flow of blood is so slow. Imagine if you had think of an example, a shower head, for example. Now the airflow inside of the shower, that one shower pipe leading up to the shower head, that's going to go really fast. And as soon as it diverts out of all of the individual holes, it slows down. Pressure drops because it's being spread out over a wider network. There's more resistance from the capillary walls, slowing that blood down. And if you had the option to try and jump into a car when it's driving past you at 30 miles an hour, not recommended, or if it's crawling past you at half a mile an hour, you've got plenty of time to open the door, sit yourself down, put your belt on, close the door up, and you're ready for the next ride. So the slower blood can move past alveoli, the more time there is for this gas exchange to occur through the surface of the alveoli. Another factor to do with capillaries, or capillaries and alveoli, is the thickness. Now, I know they've got nothing to do with magnetism, but just for analogy's sake, if you had a piece of metal and you had a magnet, the closer that magnet got to the piece of metal, the more likely it is it's going to have an effect on it and move the metal. Similarly, for our haemoglobin. Now, haemoglobin does have a high affinity for oxygen. It attracts it towards it, but not using magnetism. But the closer we can get, or the closer haemoglobin can get to an oxygen molecule, the closer it can get, the more likely it will jump on. The alveolar thickness and capillary thickness, one cell thick, very thin. So if we were to bump an alveoli surface next to a capillary surface, these thin walls mean that the gases in the alveoli and the blood in the capillary are very close. The distance between them is very short. And it means the haemoglobin has a bigger effect on the oxygen. It means the partial pressure difference, this diffusion gradient, has more effect if things are closer together. Which is what I was talking about here, this diffusion distance. The term which we need to sort of note down from this slide here is that, where is it now? Partially permeable membrane. Is it on there? No. Well, partially permeable. Don't know why that's not on there. That is what you need to put down. This one cell thickness allows gases to move through it. Partially permeable. Okay, permeable means that it permits some things to pass through it. Not all of them, but some of it. Almost like a sieve, again. A sieve blocks out most things, lets some things through. And for the alveoli and capillary, which are so thin, it permits some gases to move through, but not fluids to move through. The diffusion distance, obviously what we were just talking about there, thin capillary wall, thin alveoli lining, means that haemoglobin is very close to oxygen molecules, and CO2 is very close to that low pressure, that low partial pressure zone inside the alveoli. Now, an extra note on diffusion distance we'll look at in a moment on the next slide. But when we when we look at this proximity, the distance of blood inside the capillary and air inside the alveoli, a big factor can be cholesterol or tar. So lifestyle choices, so poor diet or lack of exercise, which can lead to a build-up of cholesterol inside these capillaries. If we eat a high-fat diet and we don't convert all of the fat that we consume, or any sort of foods, if we don't convert that calorie consumption and energy consumption into outputs, if we don't convert it, we need to store it inside of our body. One place that we might store some is inside these capillaries. So if we were talking about distance, alveoli and then capillary wall, but if we've got extra lining of fat on one side before we get to the blood, and we've got an extra lining in the alveoli of tar from smoking, we've now got 2 extra buffers between the air and the blood. We've got this greater diffusion distance to try and combat. It's less likely oxygen will jump out and attach to haemoglobin, and less likely carbon dioxide will leave the blood and enter the lungs. So to summarise those 5, 6 factors which impact on gas exchange, there is that activity sheet. So note down what they are. You need to unscramble them first. So obviously you do have the slides to help you if you can't work them out first time. But note down that impact, not just what it is, not just a description of what it is, but what's the overall impact. So yes, we know fat can build up and tar can build up, but what's the impact? And there's also a third activity or another activity sheet there, just to sort of progress you on to those extra factors. Which brings us to the end. So hopefully by now you all know the fundamentals of gas exchange, sort of how gases move between alveoli and capillary blood. Hopefully you now know and understand the role of haemoglobin, how it acts as that transporter and it helps oxygen jump on to then get transported. And hopefully we also know the importance of these structural features, these factors that impact on better or worse gaseous exchange. Which brings us to the end. So I hope that lesson and the lesson before, if you were here for the air pathway lesson as well, I hope you found those of use. Like I said at the start, if you did want to find the, where is it now? Extra resources that go along with this lesson, with the group class or the master class, wherever or whatever platform you're watching this on. If you did want more information on how you can get these slides or get the flashcards or the quiz questions that go with it, then GCSEPeportal.com is where you want to go. There's a completely free trial for the first part of paper 1 to get stuck into, to see if you like it, and there's plenty more resources where they came from if you find it of use. So I hope that lesson was helpful today. It was great to deliver it. I hope you enjoyed it, and I look forward to seeing you again soon. Goodbye for now.